Hi, and welcome back to the Low Level Devel channel's Gameboy Emulator development series. In the previous video we covered the arithmetic instructions, and in this video we're going to cover the bitwise logic related instructions. So let's get started. First, let's take a look at this the matrix of the instructions, and you see we covered these last time, and they're actually in the same format as these next set that we're going to cover. It's this AND, XOR, OR, and CP. Okay, so now we'll move over to our instructions processing code. I'm just going to copy this no-op. I'll paste it a couple of times. Let's see, we're going to have AND, then let's see, the next one is XOR, followed by just OR, and then we also had CPL. So we'll make that one, or CP actually, sorry. So let's start with the AND. So all these AND operations are being done on the A register. So I'm just going to say A AND equals the fetched data. CPU set flags. CTX reg equals 0, so we're setting the Z flag 0, 1, 0, and that's as laid out in, where are we at? Down in the AND section, yeah, Z 0, 1, 0 under AND. Okay, and that's really all there was to that function. It's a pretty straightforward one, and so is the XOR. So if we take that, paste it in here, and instead of using AND equals, we'll just use that caret equals, which is XOR. And we're just gonna make sure we just get that bottom byte. Okay, and see, that's Z000, so alright. We can again take this, use it for our OR function, and we'll use OR equals. And I think the flags, are the same on that one. And then for the CP, what we're going to do is can cast to an int A minus fetched data. So now we're just going to set the flags. If n equals 0 for Z, then we have 1. And let's see, so for the H value, we're going to do the casting again, regs.a, and with 0x0f minus the fetched data masked with that same 0x0f. So now if that's less than 0, then we will be setting, that will set the H flag. And then n is less than 0, we'll set the carry flag. And that's really just the purpose of this CP function. It's not actually changing any registers, it's just changing these flags. And something's wrong here. I think I just need to put CTX at the front. There we go. Okay, so you can see those four functions were pretty simple. So let's quickly go through and add them to our instructions map. And I'm gonna kind of just zoom this really fast because these are easy. I'm essentially copying that 9, changing it to A, changing all those to A, and let's see, change these subs to AND, change these SBCs to XOR, and then I can copy that whole thing. Actually, we have a couple of extra ones, this in AND, RD, so there's a couple extraneous ands here, or at least one. So that's E6. And then we have XOR. When we do that, XOR 1 as well. So now, again, copy this A section, use that for B, and change those ANDs to ORs and those XORs to CP. And I think that covers all of it. We do have an OR down here. E9. Yeah, definitely. And then the CP we have down here too. So, yeah, hopefully you don't mind me speeding that up. I just don't want to drudge through all these really slowly when it's pretty much just setting these values. Now this prefix CB instruction, actually we grab the next byte, and that next byte determines which of these different operations we'll be running. So it's like a whole separate instruction set just for that one instruction. And these are actually pretty easy to implement. We can do it by just kind of decoding this byte, because you see this B, C, D, E, H, L, address of HL, and then A, and it follows that same pattern all the way down, just like those last couple instructions did. So I'm actually going to create a function to handle that. Let's see. We'll call this, I'll copy that. Alright, actually first, yeah, let's have a reg type lookup. So we have B, C, D, and this is in the order that they were on those instructions types. Remember, it was B, C, D, E, L, that HL, and then A. So if we look those up by that value that they are, and then we can have a decode reg function, which essentially will just take those last three bits. So if it's greater than the maximum value of 3 bits, then we're just going to return none. Otherwise, we're going to look up that reg value. And we're going to get that value by masking it off the bottom of that CB value. Hopefully that makes sense. You'll see as we kind of go along here. So let's see. We have these. So we have these reg functions. We're actually going to create a couple of more of them. Those ones handle all 8 and 16-bit ones. This one is specific to these bitwise type functions. So we have a CPU read reg 8, which will just get A through L, and then HL is returned as a memory address read at the address of HL. So I'm not going to go in detail over this. It's similar to the other function. And bus write works in the opposite way. It'll do a write to those registers. And so let me just put those in the CPU.h as well. So these will be used by this function that we're creating. Okay, so now let's see. I'm going to grab this no-op, paste it down here, and I'm going to call this proc CB. So let's go ahead and add this to our map at the bottom. So in CB, or actually we got to add these other ones first. We'll do AND XOR, and then we did OR and CP. Okay, so now we can add in CB, equals proc CB. In this proc CB function, we're going to essentially decode that second byte that comes right after the CB instruction. So the operation equals CTX fetched data. That's going to be our byte. Now the reg type is going to be decode reg. We've got that op and mask those bottom 3 bits. So that'll give us whether it's going to be a B, a C, a D, a E, HL, address of HL or A. And you can see that repeats for all these. So that's the way we kind of decode which register is being used by this operation. You can see even down here the set one uses that same format. All these different operations use that format. Okay, so we have our operation, our register that we decoded from it. Now we need to figure out which bit is being used. So if we look down here, we have reset 0 and then reset 1, reset 2, reset 3, and the same with bit up there, and then the same with set as well. So sets all follow that same pattern, and so do the bit ones up there. So this is how we figure out which bit is which bit is being worked on. So we just shift it over by 3 and then mask those bottom 3 bits. Now which operation we're doing, we're going to shift it over by 6 and mask the 2 bottom bits. So that's going to be whether it's RLC, RRC, RL, RR, swap, SRL. So that's going to be, let me go back here. Yeah, that's going to be the bit operation that we're performing. So let's first add an EMU cycle. And now we're going to say if the register is equal to HL, that's the one where we have one special thing that's happening. So we need to add 2 EMU cycles to that. And now we're going to switch the bit operation. So which bit operation are we running? In the case 1, we're running the bit operation bit. So I'm just gonna quickly add these. So bit RST, which is reset. So we have set. Actually, we can return instead of just breaking. So that's bit, those are bit, and then we have reset and set. Okay, so for bit, we're going what this function does is it gets whether or not the bit is set on that register. And how do we get it? We get it by using flags. So we have 0, 0, and 1 are the flags that we use. So the Z flag is the important one here. They're all actually important, but that one is the one that really determines whether that bit is set or not. So we're going, if the bit is set, we are going to set that 0 flag. Actually, let's grab the reg value. So we'll CPU read reg 8 on that register. So if not, okay, if not reg value 1 shifted over by bit. So if that is not set, then the Z flag will be set. Okay, and that's really all there is to the bit function. So for reset, we kind of just want to reset that that register's bit, the bit on that register. So I'll say reg val and equals tilde 1 over by bit, and then we'll call CPU set reg on the reg and the reg val. And set is pretty much the same, except we do OR equals with just 1 shifted over by bit. So that will set that specific bit on that given register. So if it isn't one of those 3 values, then that's when we move on down here to the next section. First, I'm going to just grab the C flag, put it in a variable, make it easier to use. Now I'm going to switch the bit that's being worked on. In the case of 0, this is going to be an RLC. And we can break. Or should we return? Actually, I'm going to put it in in these, and I'll say return. So then we have 1 is going to be our RC. Yeah, so we have RLC, RRC, RL, RR. Okay, let's go back here. RRC. So RL. RR. Okay, paste again, and then we have 4, I believe was swap, no, or SLA. And then SRA. Okay, so 6 is going to be swap. 7 will be the last one, I believe, SRL. Okay. So we're going to start with the RLC, which is rotate left, old bit 7 to the carry flag. So to start this off, we'll say set C is false, result equals reg val shifted to the left by 1, and with 0xFF. And now if reg val masked with 1 shifted over by 7 is not equal 0, so if bit 7 is not set on the reg val, then we will say result OR equals 1 and set C equals true. So now CPU set reg 8, we're going to set the register to the result, and then CPU set flags, so result equals 0, false, false, and set C. Okay, add CTX to the front of that. Okay, so that's all for the RLC. So now moving on to the RRC, which is rotate right, old bit 0 to carry flag. So we get the old value, then we shift it over by 1 to the right. Then we OR equal it with the old value shifted over by 7. Okay, set the value for it. And set the flags. Not reg value, false, false, and the old and 1. So that'll tell us whether the C was, the carry flag was used. Okay, so now rotate left. That's the RL. And this is pretty much going to do almost exactly the same. Shifting it over by 1 to the left, ORing it with flag C. And I think we can take this whole section and paste it. And this will be replaced with not old and 0x80. So if that high bit is set. Okay, so then rotate right. So grab the old value, shift it over to the right one. And then the reg value we're ORing with flag C shifted over to the left by 7. And paste these. I think that can stay as is. Yeah, looks good. Alright, so now SLA, which is shift left into carry, least significant bit is set to 0. So red value shifted over by 1 to the left. And let's see. So we can reuse a lot of this. There's probably a more elegant way to write this stuff, but you know, for now this works for the purpose of this tutorial video. So now moving on to SRA, shift right into carry, and the most significant bit doesn't change on this one. So I'm gonna say U equals reg val, U equals U, shifted over by 1. I think I need that int 8t, right? Yeah, reg val. Sorry about that. So U8U equals int 8t reg val shifted over to the right by 1. So now that we have that in the U field, so we're going to just CPU set reg 8, reg, and U. Not U, 0, 0, and reg val and 1. So that's another simple one. Okay, now moving on to swap. So swap is essentially, we're going to take the high nibble and swap it with the low nibble. So yeah, so and with F0 shifted over to the right by 4, or that with and 0xF shifted over to the left by 4. Hopefully that makes sense. We're swapping the two nibbles of the byte. And now we just call CPU set reg val. And this should be a simple one too. Let's see, CTX reg val equals 0. False, false, false. And I think we got one left. Yeah, Z000. So, and then SRL. So this is shift right into carry. Most significant bit is set to 0. Okay, so U is equal to reg val shifted over by 1 to the right. And we'll just call that set reg 8. and set the flags to not U, 0, 0, regs val, and 1. And that should be all of the different options for the CB. And if for some reason it got down to here, I'll just print out an error. Yeah, I don't think that it's actually possible to get down to here, but for now I'll just say invalid CB. Let's see, put in that op code, and I'll just say no info, so we just terminate from there. Okay, so let's do a quick sanity check. I put this down here and CB. Okay. Now making it, we see one error. Proc XOR. Let's see. Oh, I have it in here twice. I don't know if that's what it's complaining about, though. Yeah, let's see, proc OR as well. Regardless, I'll remove that, but let's go ahead and make again. And let's see. Oh, we have two XOR functions. That's probably why. Let's remove that. They should be doing exactly the same. Yeah, I forgot we implemented that pretty much at the very start. Okay, CPU read reg 8. So that's because in here I think we need to add bus read, or the bus.h, so we can read the bus and write it. Clear make. Okay, now it looks all good. Now let's rerun one of these CPU instructions. So invalid instruction CB, that doesn't sound right. We must have missed something. Oh, yeah, I didn't add it here. Okay. CA, this is pretty much simple, just IN CB. In the addressing mode, we need to get that first byte, so I'll just say, let's see, AMD8. And yeah, I think that's all we need. Okay, and make again and run, and there we have some CB instructions we're getting called. So those are getting invoked. I'm not validating them yet. Let's see, what's this 1F? That is RRA, and I think we'll get into that and some of the special ones in the next video. So I think that's probably a good stopping point for this video. This kind of gets us through most of the instruction set for the CPU. There's really only a few instructions left we haven't touched, and then we got to do interrupts, and then we can run some CPU tests on it. I updated some more ROMs in that ROMs folder for a bunch of individual CPU tests that we can start running in the next couple of videos. So I hope you learned something from this video and enjoyed it, and please like, comment, subscribe, join our Discord server, and thanks for watching.